All right. So this week, we started last week talking about how the neurons fire, they develop and they kind of spread throughout our body, right, to activate our pain receptors. Our pain receptors activate our sensory receptors in our brains, right, to tell us, hey, there's something going on. We also use neurons to form vision. If we see something on the outside, it triggers sensory receptors within our eyeballs, and then produces those electro signals to our occipital lobe, our visual cortex. Okay, so all these things happen in kind of like a hardwired context. But what we're starting to kind of get into now is, how do we get all this stuff that's happening on the outside into our brains for processing, right? Because we know kind of how things work as far as how they're connected, but now we're going to start picking up on how we get information into our brain. And we already talked about like ESP not necessarily being the preferred way of getting information in our brain, because we can't really study that. We can't really manipulate that in any way. So we have to rely on our five senses. And we're going to go through them systematically through this lesson. But the purpose of this lesson is twofold. And today we're going to primarily focus on how our five senses take in that information. And unfortunately, this week, we're not going to have time to really cover how we process that information, but I have lots of videos that kind of talk about perception. So two things we're talking about this week: sensory and perception. Today, we're going to focus on sensory, and perception being how we deal with those signals and make use of them. Okay, so I'm going to share my screen with you. And bring up my slide. Okay, so go through some of these slides here. I'm going to breeze through a couple of them just for the sake of getting through them and getting to all five senses and how we deal with those. Okay, so with our sensation portion of it, how do we take information in? What senses do we use to get information from the outside into our brains? Sight, hearing, okay. Touch, absolutely. Smell and taste, absolutely. Got all five, okay. So that's how those are the sensory receptors that we have in each of those five areas. Some of them are localized, right? Because we can't really see through our kneecap, for example, right? For a couple of reasons. First of all, we wear pants, and anybody that has eyeballs down there, that might be a different story. But for the most part, we have localized sensory receptors, like our eyeballs. Okay, our hearing is localized. Our sense of taste and smell are localized, right? Well, what about touch? Touch isn't really localized, is it? It's all throughout our body. We have pain receptors, we have pressure receptors, we have touch receptors. They're all throughout our body. And some are more localized than others. Like we may have more receptors within the tip of our finger than we would, say, on our arm, or maybe even on our scalp, which has even less. So I like to start off with this little. Now, we don't have very many people in this class, but hopefully we'll get a little bit of difference in opinion as far as what we're seeing here. What colors do you see in that dress? You see blue and black? Okay. Brown and lavender. Okay. Okay. So you're probably right on the cusp of like, so some people will say that this is white and gold. Have you seen this before? Okay. Okay. Some people would call this white and gold. I see blue right here, the blue, and then the black lace here. So this image was produced probably around 12 years ago. A woman in Scotland was getting married, and she sent her bridesmaids dress to her bridesmaids, who were still, I believe, stateside or something. And none of them, not all of them agreed on what they saw. Some of them saw blue and black, some of them saw white and gold. And what this is, what we come to learn, this became really a media sensation. It was on the TVs, it really went viral. There's not a lot of people could really agree on what that is. And it seems to be somewhat divided. But what is happening here is our cones, this is on the cusp of what our cones can see and cannot see. So some people might be able to see this range where they see white and gold, where some people don't have those sensory receptors activated, and all they're seeing is blue and black. Okay, so this just kind of demonstrates how we're able to really each one of us are a little bit different. Okay, now I've never heard, what do you call it, brown and
brown and it looks like a
lavender. Okay. Okay, well that's a new one for me. I haven't heard anybody say lavender.
Like the base is like completely black.
For me, it is. Yeah, for me. So you see it as what, lavender?
Like a sack brown.
Interesting. Okay. Okay. Well, that's a new one. I don't think, I think you're the first one that I've ever talked to that said that. Interesting. Okay. So anyway, this is just an example of how each one of us has something a little bit different. Now I put this term up here, synesthesia. This isn't anything you really have to concern yourself with. This is just kind of an example of where things kind of go a little differently for some people. Like, for example, synesthesia, when we're talking in terms of transduction is just what I was talking about earlier. We're taking the outside world through our senses, and then we're processing them mentally, and then doing something with that. We're either reacting to that, or we're forming memories or something, right? Where it's just transduction, put simply, is taking the outside world and bringing it in. Synesthesia, however, is the act of transforming or acquiring that information through one sense, but it activates other senses, if that makes sense. So what do I mean? I'll give you the definition first here. So sensory information processed differently in wrong cortical areas. So for example, if you heard like Mozart's Adagio or something like that, or Marriage of Figaro, and you were able to produce colors in your mind, you were able to see it in terms of colors as opposed to hearing it in music, that would be an example of synesthesia. Okay, does that make sense? Okay, so that's like just converting one stimuli into another, one sensory into another. One of the things I like to use when I'm doing therapy is helping people with relaxation and using guided imagery, asking them to imagine breathing in cool, calm, positive energy, and then gathering up all their negative energy and breathing it out. So for example, if I asked, what color would you imagine breathing in calm, like calm, positive energy, what would you say? Green, okay. Blue, okay, okay. How about negative energy? Red, black, okay, all right. So we each have something a little bit different. But, and while that's not necessarily synesthesia, now if you did that automatically, if you believe that you were breathing in blue air and then breathing out black air, that would be synesthesia if you were able to taste that. Does that make sense? Okay. And again, that's just an example. So again, sensation is the activation of receptors in the various sense organs, as opposed to perception, which would be a different lesson, is taking that information and doing something with it, in some kind of mental process. Okay. So within sensory thresholds, so it's important to understand how our thresholds and just noticeable difference actually work, okay? Because we don't acquire everything that's going on around us, right? Do we? We might be able to be aware of it, but there are a couple things going on. First of all, we have to be able to detect it. If we are able to detect it, are we processing that in some way? And that's, again, we'll go into perception. But for the very basic, in order for it to enter our brains, we have to be able to detect it. And we use two processes, one called absolute threshold, and the other one is just noticeable difference, okay? So absolute threshold would be the bare minimum amount of energy for a person to detect that stimulus 50% of the time. How many of you have had like an auditory test, had your hearing checked? Okay, both of you. Okay. So what happens? Describe to me what happens with the hearing test. What are they? What is it like? What are they doing? What are they trying to detect?
It's like they'll put on the headphones and they're going to play a sound. They're like each one of your ears normally isolated, and then they'll like ping and see like what the lowest frequency is you can hear.
Okay. So you have to respond when you hear a tone, right? Do you always hear those tones? Do you hear every one of the tones that they produce? Okay, probably not, right? That's what they're checking for. They're trying to see, number one, what's your lowest frequency that you can hear? What's your highest frequency that you can hear? What's the amplitude that you can hear? And are there any gaps in between there? And what they're trying to find out is, do you have any kind of hearing loss, or is your hearing less than what would normally be acceptable for somebody your age? So what they're doing on each one of those high end or low end is they want to see 50% of the time, can you respond when you hear that? Can you hit that clicker when you hear that that tone? And if you can't, if it's less than 50%, they usually discontinue going any higher or going any louder. Okay. So that's really what absolute threshold is what is the amount of energy it takes for you to be able to detect that hearing signal. For sight, it might be maybe you're in the dark and somebody lights a candle a mile away. Are you going to be able to see that? Maybe. It really depends. It might depend on humidity. It might depend on how big the candle is or how big the flame is. It might depend on how good adapted you are to the darkness. That might produce something you can detect. Okay, as they move that closer, and you say, "Hey, now I can see that," and then they keep doing it at that distance 50, and you respond 50% of the time, that would be absolute threshold. Okay. So just noticeable difference. I used to do a little classroom experiment with my bigger auditoriums where when I had a sound system is I would play a really low noise, a really low pitch. And it was just kind of a hum. And every time I'd walk up to the podium, I would turn it up a little bit more and turn it up a little bit more until about a half an hour, I had that thing cranked pretty loud. And I'd ask anybody if they heard the tone, if they were able to detect the tone. And then they're like, oh, now I hear it. What I was demonstrating in that moment was being able to change something that they were acclimated to and see if they really knew if anything was changing. Okay. So what just noticeable difference is referring to is how much change needs to occur before the person can detect that change is occurring. And maybe some of you have done that with your parents or your siblings or your friends, where maybe you're turning up the radio a little bit louder because you want to hear it, but you don't want them to know that you're turning it up. That would be an example of just noticeable difference. If they were able to detect that you were changing that sound or that level of that volume, then they were engaged in JND, or just noticeable difference. Okay, are we pretty clear on the two of those? Okay, so threshold is the minimum amount of energy for us to detect it. JND, or just noticeable difference, is the change significant enough for us to be able to notice that a change is occurring. Okay. All right, and these are just some examples of absolute thresholds. You know, like maybe a bee lands on you versus maybe a mosquito. Like the mosquitoes here are not detectable. Has anybody noticed that? I came from Alaska, and if a mosquito landed, in fact, we kind of joke around, the mosquito is the state bird of Alaska, because those things land on you, your whole shoulder goes like boom. You know, so they're big, they're heavy, and you can just kind of feel that because they activate more touch receptors than do maybe a smaller gnat or mosquito here in West Virginia. Okay. Vision, we talked about what absolute threshold would be. Hearing, maybe a faint ticking in the background isn't enough to get our attention, but a grandfather clock would, right? All right. Another term that your book likes to use is subliminal stimuli. So these are referred to stimuli that are just below the level of conscious awareness. So they're occurring, but at a level that we're not really aware that it's occurring. What are some examples that you have of subliminal messages that you may have seen in the press, in the media, or read about or heard about? Have any ideas of subliminal, anything that might suggest that you do something without you actually thinking about doing it? You think of anything? How about advertisement? Okay. 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 Yeah. Something being in the background. Like here we had what did it say? Eat popcorn, right? How many? I mean, I don't know if did anybody all of a sudden get hungry for popcorn by any chance? If that actually works or not, but that would be an example. And they have had a couple companies that were implicated in history, throughout history, like usually around the 70s and 80s, of putting like drink Coke, for example, in their TV advertisements. And sometimes that works. Sometimes it doesn't. And in advertisement, what they were finding when they were doing like the quick little flash is we have to be able to process that. We have to be able to absorb it and see it and read it. Because if we don't, then it doesn't really work. So that's kind of the criticism of subliminal stimuli, is that it has to happen in a way that we can actually process it and see it. Otherwise, it doesn't really work. So flashing drink Coke doesn't really work unless we were able to somehow read that and be aware of it. Okay. But we might see this in advertisement in terms of, did you want me to turn back the lights? Turn them back on, or we good? Okay. But we may see that in terms of selling attractiveness, right? Like people that drink this product might associate with attractive people, right? Very symmetrical, visually appealing people, which might make us, because we all want to fit in, right? So these are types of messages that advertisers might use subliminally to appeal to our senses of buying their product. Okay. And we'll talk more about that when we get into social psychology and attraction. All right. So habituation and sensory adaptation. So there's really a difference between the two of these, and I'm going to do my best to explain these. Okay. So habituation is when the brain stops responding to something that's going on in your environment. So for example, how many of you grew up with like a grandfather clock or, okay. So what happens? Do you ever really notice that grandfather clock ticking away? Okay. So if it were to stop, would you know it? Like if you didn't hear that, you walked in the house and all of a sudden, and it just wasn't working, would you know that it wasn't working? You probably wouldn't pay attention because you're used to hearing that, right? I got a great example because we have our beloved clock tower out there that dings away. You're right. And I first got here a while ago, and I'm just thinking every time that thing rang, I heard it. Even on weekends, for some reason, at 7 o'clock on the weekends, that thing goes off, and I can hear it very clearly in my house. Sunday, I was outside pretty much all day, and I noticed that like 4 hours had gone by and I hadn't heard that bell. Okay. Did that mean that it wasn't ringing? Probably was, right? But habituation, I became so used to hearing that it just became commonplace to me. I didn't really pay attention to it anymore because cognitively I was adapted to that. It became part of my habit. And you're going to hear me refer to humans being two things. You're going to hear me refer to this a lot in this class. So kind of build it into your mind because it really fits in all that we do. As humans, we are two things. We are both lazy and we are both proud. Okay. I use the word lazy lovingly, okay, because I'm not saying that we all just want to shirk our responsibility. When I say lazy, what I mean is that we like to create routine, don't we? We like things to be easy. We want things to be simple. It's our human nature to simplify things. That's why we have smartphones, because it makes our lives easier. That's why we have cars, because it gets us to where we need to go a little quicker, all right? We as humans like things easy, and we do this for a very good reason. It's part of our nature to free up our mental energy so that we can focus on important things like survival and eating and maybe even a threat to our environment. Okay. So when I say that we're lazy, it's that we're just trying to create a routine. And you're going to see that sprinkled throughout this course, is that we create routines. When we learn, we're creating how to do something again and again and again, because it either produces a favorable result or it avoids something negative. So that's what I mean by lazy. And when we get into personality and defense mechanisms and learning, we'll talk about pride and motivation. We'll talk about pride a little bit later. But for right now, just kind of keep in your mind that we like to keep routines. And that's what habituation is us being able to create a routine so that we can focus on something else, okay? Now, if a different bell rang or a different type of chime happened or it came from a different direction, I might be able to notice that, because now we have something that's a little bit changed, right? Okay, so that's habituation. Sensory adaptation, however, that's not necessarily getting used to the sound. What that means is that the sensory receptors are becoming less responsive. So it's more of a biological explanation as opposed to a cognitive explanation. So for example, say you, like every weekend, you go out to like a mosh pit or something. You stand right next to the loudspeakers and you're hearing that blasting music. And after a while, you're starting to hear less and less high pitch, like maybe a female voice or something, a higher pitched female voice. You're having a hard time hearing, okay? That would be an example of sensory adaptation, because your senses aren't actually picking those up anymore. Does that make sense? Okay. Another example would be for pain receptors. So say you put a pin in your arm, okay? That's going to hurt. You're going to feel that a little bit. But after a while, what's going to happen? You'll get used to that, right? So your sensory adapter, and there's probably a little bit of both going there. You're probably realizing that that's not a threat, so cognitively you're ignoring it. Your sensory adapter is always picking your adaptation. You're always picking that up. It's always there. So it just says, okay, I'm not going to fire off pain signals anymore because it's just residing there. Okay, so you probably have a little bit of both going on there. Okay, so that's really the difference between habituation and sensory adaptation. All right, so let's go through quickly our five senses. Okay, so the first one, I like to use this as an example. So my first one is seeing. Our sight has evolved over many generations, over thousands of years, to where we are today. Okay, what was important for survival 5,000 years ago isn't necessarily. What's that? Yeah, well, yeah. Many of our senses have adapted or have evolved over time. But our sight has, in particular, is not what it used to be 5,000 years ago. And that's by design, because we don't really require, what natural predators do we have as humans? None, right? We don't really. We have some threats out in the environment, but we haven't passed on those genes to be able to see black and white. So I use this as an example. Now I know you probably have a little bit of a glare over there, so I'm going to see if I can. So can you see, either of you see a threat in that picture there? Nothing? I will tell you, if you were a dog or a deer and you had better night vision, or even a cat, and you had better rod receptors in your retina, you would pick out the threat in that immediately. But we as humans, have not really, we don't have that need. We don't have the need to be able to see in a background like that because our survival doesn't depend on it. So kind of look in that area that I have highlighted and tell me what you see now. You see it now? Nothing? Can't see it? Right there, a panther, right? You see it? You see it now? See, as humans, we wouldn't really need that ability to pick out something from a dark background like that. But but if our survival depended on it, you better believe that would be an important thing. Kind of freaky, isn't it? Yep. He's waiting to pounce. So that's just an example of our adaptation through thousands of years. So really quick, I'm not going to go much into the science of it, but just know that our visible spectrum goes right around 400 nanometers to about 750 nanometers. Low end would be the ultraviolet, and as we get up to the higher end, that would be the infrared. Okay, I'm sorry, infrared going to ultraviolet. And again, right here on the spectrum, we have ultraviolet on the low end, infrared. I'm sorry, I got it backwards again. Ultraviolet on the high end, infrared on the low end. Of course, radio waves would be to your right. The higher frequencies like X-rays and cosmic and gamma rays would be on our left. So our range is right before ultraviolet and right after infrared within that visible spectrum. Now, what happens, again, I'm kind of just rehashing some of your old science classes. So how do we produce light? Like I'm holding up this can here. First of all, can you both tell me what color that can is? So how does light occur? How are you able to see a red can? The what?
Like the cells on the paint.
Okay. So what's happening is we're getting a broad spectrum light through probably the sun outside or whatever light system we have in here. So it's kicking out this full spectrum from purple or from red all the way to purple. Okay, and we're seeing these colors. So whatever material this can is made of, whatever paint we put on there, is absorbing all those other colors, and it's kicking back all the red. Okay, so it's reflecting the red off this can, and it's absorbing the other colors, so we're not seeing those colors. So your eyes have sensory receptors within the cones that are capable of detecting whatever color is being kicked back, as long as it falls within that spectrum. Okay, now we're obviously not going to be able to see infrared. We're not going to be able to see anything ultraviolet. If radiation was being absorbed in this can, we wouldn't be able to see that because our eyes can't pick up on that. Okay, so that's just briefly how color works. And when we get into cones, which we'll talk about here in just a little bit, our cones are the ones that absorb the color. They detect the color in that paint can. The rods will detect black and white, okay, and better suited for lower light conditions. Just really quickly, some of the psychological properties of light is we look at the brightness, and that really corresponds to the amplitude. And when we get into sound, this will be the same thing. We look at color. What are the wavelengths? So with sound, that'll be pitch. Is it high pitch or low pitch? And then we have saturation, the purity of that color. Okay. All right. So basic structure of the eye. If you remember from biology, the light enters what? Right. Comes in through our lens. Our pupil, based on the level of light, adjusts to allow more light in, less light out, whatever. And then the lens reflects it back on in through our eye wall into the retina, which is the back of the eyeball here. Okay, Now, the back of the eyeball, that contains those cones and those rods I was telling you about. So it's going to produce a sensation back there that is going to fire through our optic nerve into our brain, and our brain is going to assign that an image that we've either seen before or something we're familiar with, or maybe it's something we're not familiar with at all. And it's going to make us pay attention to a little bit more, okay? So within the eye wall, what we have happening, and I'm not going to go into nearsighted and foresightedness, but this is a great image to show you how the clock, we know it to be upright, but it projects on the back of our eye wall, on our retina, as upside down. Now, why does it do that? Why does it matter? Does it even matter that it's upside down? Probably not, because we're going to perceive that stimuli to be whatever we need it to be. In fact, there's some really cool experiments out there that they give people upside down glasses, like inverted glasses, and have them try and function for a week with those inverted glasses. How do you think they did?
Probably okay.
Oh, yeah. Because what happened is it actually produced it right side up, which told our minds that it's upside down, because we're used to seeing it a certain way. So when we invert this actual image and it produces it right side up on our retina, then we're able to process that after a while and just say, hey, that's just how it exists now, okay? And what they were finding is initially, like the first day or two, people with those inverted glasses were having a hard time functioning. But after a couple days, they're functioning normally because their mind has rewired and relearned how to do everything in reverse and upside down, okay? All right, so on the back of your, what they call the fovea, your fovea is going to be your area that is going to detect your images. So let me go back to, I don't know why it, okay. So here is your field of vision as far as your day vision, okay? And when it gets a little bit darker, your color goes away and your rods are more activated. Your pupil dilates and gets a little bit bigger so it can let more light in, as whatever light's available, to help activate your rods, okay? So your rods are important for night vision, your black and white, because we don't have any light coming in and reflecting, right? So we don't need to really pay attention to color. We need to pay attention to distance. We need to pay attention to maybe some movement, and quite possibly we would be more interested in shapes of things, because that's going to help us determine what's going on in our environment. Okay, so very important. Cones deal with color and day. C for cones, C for color, and rods are for night vision and black and white. And this is just a representation of your visual pathway, okay? So your left field of vision tends to be primarily occurring on your right visual cortex, as you can see here, okay? Whereas your left field of vision is, so in the back of your occipital lobe, which we learned about last week, contains your visual cortex. Why do you think we have two halves? Why do you think we have a left cortex and a right cortex? Okay. More importantly, why do we need to be aware of what's happening in two eyes? What do two eyes produce for us? Kind of vision. Okay, 20/20. So the ability to see at a normal distance. Okay. How about binocular vision? Binocular meaning by, two. Okay. So when we have binocular, we're able to detect what? Depth. Right? Depth. So we can see kind of both sides of it, and our visual cortex compares and contrasts what each eye is seeing to tell us how far that item might be away from us. Now we have when you get into cognition, we have other cues, like what we assume to be a normal sized person or normal size baseball or normal size room. So we can play tricks on our mind that way. But for the most part, the reason that we have a left visual cortex and right visual cortex is to help us determine depth of whatever it is that we're trying to see. Okay. All right. So dark adaptation, light adaptation. This occurs when your pupil has to dilate or constrict, or if you need to get time to activate your rods and your cones versus your cones. So many of you, I'm sure both of you have probably gone from a dark room into a light room. What happens?
Your eyes get irritated.
Right. It takes a while. You're like squinting because your pupils are dilated. You just got used to a low light area, and now you're in a bright area. And then what happens when you go back to that dark area? You're blind. You're tripping over stuff, right? So it takes probably around 30 seconds to maybe even a couple minutes for some people, depending on their situation, to adapt from dark into light. Okay. All right. The last thing I'm going to cover today, because I know we're running up on time, is trichromatic theory. Some of the theories that we have as to what colors we see and how we produce. Because again, we don't have little electrons that we can hook up to our retinas, right? We don't have that kind of capability. But we do have some theories as to how that works. And the first one of them is the trichromatic theory, which posits that we see things very similar to how we produce. Have any of you seen like those old Ray televisions, the big tube televisions? Have you seen those? Okay, I don't know how long it's going to be until I don't see those anymore, but we use the very same principles in those tube TVs where they fire a blue, green, and red. And depending on the strength of either of those and the areas that they're producing, they can produce an entire spectrum of colors. Okay, and we know that. We've all been to art class or paint class or something like that. And what happens when you mix colors? Right. So if we add a little bit more red to white, we're going to get like a dark pink. Or if we add more white to, so on and so forth. But trichromatic theory states that we see variations of those three colors: blue, green, and red. And it just depends on how they come across those cones as to what color we actually see. Okay. The other one that we have is the opponent processing theory, which suggests that we have two types of cones, either a red-green one or a blue and yellow one. And if one is activated, then the other one is less activated. So if our red-green cone is activated as red, it's going to see less green. But as soon as we take away that red coloring, then it's going to bounce back to whatever the initial state was, which would have been green. Now, one of the ways that I have to really demonstrate this, actually, let me see if I can go to this lecture activity. All right, is after images. So this is a demonstration of the opponent processing theory. All right, so if you look up at the screen, focus on that white dot. Okay, give you about 20 seconds to focus on it. And then stare really hard at that white dot. What did you see? What did you see after it changed? You just saw white?
Yeah, I definitely saw the stars.
Did it change colors for you? So try it again. Let's stare at it again. Did you see red, white, and blue when it disappeared? Okay. That's the opponent processing theory. And it's stating that this green, as soon as it disappears and floods your eyes with white, it turns to red. This yellow turns to blue. Okay. And then, of course, the black turns to white. Those are your cones and your rods being processed there. Okay. So, let's see, return to lecture. All right. So that's the opponent processing theory in after images. All right. I think we're running up on time here. I do have these slides available online if you want to go ahead and follow up with your other four senses. Unfortunately, we don't have time to go over them today. Were there any questions that you had for me? Anything at all? All right. Well, if